Hello again. We are continuing our discussion of convolution in this video, and we just completed exercise 1 in the previous video, and we saw there that we could solve this introductory initial value problem if we had a right-hand side of t. But in that case, that was simple enough. We could have used other methods to solve it. We wouldn't have had to use Laplace transforms, and even if we had done Laplace transforms, we could have done it without a convolution if we had wanted to perhaps use a partial fraction decomposition on the right-hand side or something like that. But if we wanted to avoid Laplace transforms entirely, we could have. We could have done it with information that we know of for second-order linear differential equations, and we could have used either variation of parameters or undetermined coefficients in order to get our particular solution. But what happens if we want to consider a general right-hand side? Let's say we know we have a forcing function, we just don't know exactly what it is, so we want to be able to find a solution in terms of any general right-hand side function. Well, we can't do that with other methods, but we can do it with Laplace transforms and convolution. So that's what we're going to do in exercise 2. We're going to solve the introductory initial value problem with a general right-hand side. We still have the same initial conditions though. So going back to what we had from the introduction, we had that y of t was the inverse Laplace transform of 1 over s squared plus 1 times capital G of s. So we're going to use the convolution theorem. And we need to identify what our functions are. So first off, we're going to identify big F of s as this first function, 1 over s squared plus 1. So that means then that f of t, which is the inverse Laplace transform of that, is the sine of t. Our second function for our convolution theorem is g of s, and that's just the Laplace transform of little g of t, our right-hand side function that we don't know. So that means that g of t is just the inverse Laplace transform of g of s. So then we're going to use the convolution theorem, which says that the inverse Laplace transform of these two things, so that's what y of t is going to be the convolution of little f and little g. So little f is the sine of t. We plug that into our convolution definition, and we have the sine of t minus v. G of t is just what we have there, so we plug v in there, and we get the integral from 0 to t of the sine of t minus v, g of v. So this is exactly what our solution looks like. Now, the downside is that we don't know what g is, so we can't integrate this. But it's still a formula for our solution. It's not just a general initial value problem. And we could actually find what the solution is at a particular value t by substituting in that t value if we have a specific g of v. So what I mean by that is this. If we wanted to know what y of some value is, t0, maybe it's 10, maybe it's 100, whatever, we could plug that in as our upper bound. And then if we had a certain g, we could plug that in here and integrate. And since this is a definite integral, we could either find an analytical value, let's say using integration methods from calculus, or we could use numerical integration to approximate the value since it's a definite integral. So this is a very powerful piece of information for a general solution to this initial value problem. And this is something that we can do with Laplace transforms and convolution when we would not have been able to do that with other solution methods for second order problems.